Hello. In this lesson, we are going to cover an introduction to stoichiometry. The key questions that we're going to investigate are firstly, how do chemists use balanced chemical equations? Now, you already know how to balance a chemical equation. Now we need to look at what is the significance of a balanced chemical equation. What information does it contain? What questions can it help us answer? And how can we get the most use out of that balanced chemical equation? Secondly, when discussing balanced chemical equations, what quantities can we use to interpret that equation? So, an example might be moles or atoms. Truthfully, the answer is there are a number of different ways, and what we need to do is clarify each of those ways to discuss balanced chemical equations, and then make sure we understand them in such a manner that we won't confuse them or intermix the different terminologies and get confused when looking at a balanced chemical equation, and most importantly, then not derive the wrong information. To define stoichiometry, we'll say that it is the calculation of quantities in chemical reactions. Previously, you have looked at predicting the outcomes of certain types of reactions and figuring out what the products will be in terms of types of chemicals. Now we're going to add another layer on top of that. We are going to determine how much of the products are formed. Conversely, if we have a goal, so a number of moles of a product that we want to get to, we can determine how many or how much of each of the reactants we need to put into the system to get the desired outcome. It's kind of like bookkeeping for the chemical world. If we want to use the analogy of an accountant, we can say that this is really keeping track of the debits and credits, or the money coming in and the money going out. In this case, instead of money, we are going to be using chemicals, or atoms, or moles, or whatever representative particle we happen to be working with. So we're going to look at the atoms going into a chemical reaction, and then, just like in accounting, make sure it balances out on the product side, or the output. We can use molar ratios to predict or calculate the amount of product that is formed when we put certain amounts of reactants into a system. So chemists use balanced chemical equations as a way to calculate how much product is formed or how many reactants are needed to get a desired amount of product. We are going to use the analogy of bicycle production to take a look at this and hopefully provide a little bit more clarity. I've written the balanced equation for the production of a bike, and I've simplified it a little bit, but I've said that if you take one frame, one seat, two pedals, and two wheels, put them together, it will create one bicycle. I think we would define this as a combination reaction, as we are taking multiple reactants, combining them, and forming one product. So if we look at this, the molar ratios are derived from the coefficients. You can see that the frame, the seat, and the bike all have a coefficient of 1. The pedals and the wheels have coefficients of 2. Now, one of our goals was to look at what type of things or what type of questions can we ask to get a useful outlook or to decipher useful information. So are we going to look at being given a certain number of one of the reactants and figuring out how many products we can form, or seeing if we want to get to the goal of a certain number of products, how many reactants do we need? We're going to start out with this question. If there are 23 pedals and an excess of wheels, frames, and seats, how many bicycles can be made? When looking at questions, even usually that have chemicals in the question, you are going to see the term excess very often. What that means is we know that there are an excess of wheels, frames, and seats. That means we don't need to worry about how many there are. There are enough. For however many pedals we have, there are extra wheels, frames, and seats. You are always going to perform your calculation on what's called the limiting reactant, and we'll talk about that a little further down the road. But if something has an excess, it is not the limiting reactant. So in this case, we want to use pedals. Um, we'll start that question in just a moment. The second question that we could ask is, if we want to produce 250 bicycles, how many of each part will we need? With a simple chemical equation like this, you can probably do these calculations in your head. We are going to go through and look at them stepwise to make sure we have the process down for when you move into more difficult problems using chemicals as opposed to bicycle parts. So let's approach the question: if there are 23 pedals and an excess of wheels, pedals, and seats, and that should be frames, I apologize, how many bicycles can be made? Well, we're going to start with the given information. We have 23 pedals, so we'll start with that. We write what we know. Step 2 is times in a line, so I'm going to put a multiplication symbol here. Next, we want to cancel out pedals, and ultimately our goal is to be in bikes. Alright, so we put pedals on the bottom and bike on top. Then, using the molar coefficients, we can make a molar ratio. So if we look at our balanced chemical equation, the coefficient next to bike is 1. So in this conversion factor, we put a 1 next to bike. If we look at pedals in the balanced chemical equation, we see that the coefficient is 2, so we will place a 2 next to the pedals. This allows us to cancel off pedals. Next, we need to look at, are we where we want to be? What is the question asking? In this case, it's how many bikes can be made. If we look at our units, we would now be in bikes, so we can put an equal sign, go through the calculation, and the answer is 11 bikes. It's not 11 with a remainder of 1, although there would be 1 extra pedal. We can make 11 complete bicycles. If we want to produce 250 bicycles, how many of each part will we need? Go through, and I would try and do one of these. You don't have to complete it for every single part, but pause the video and attempt to do one of them. When you've finished, unpause the video. Okay, hopefully you found great success in this. Again, we're going to start with what we know. In this case, it is 250 bicycles. Times in a line, and this next part is going to depend on which individual part you chose to convert to. I'm going to choose wheels here. So we put bicycle on the bottom and wheels on top. Bicycle goes on the bottom because we're canceling it out, and wheels is what we're trying to get to, so we put that on the top level. The coefficient for wheels is 2, and the coefficient for bike is 1, so we put a 2 on top and a 1 on the bottom. An equal sign, as we are in the correct unit for the end of our problem, and solve it. 500 wheels. Interpreting balanced equations can be complicated, as there are a number of ways to do it, but as long as you keep track of each of the ways, we should be in good shape. We're going to use this equation to look at balanced chemical equations. This is the reaction for the production of ammonia. To give you this reaction in just English words, it is 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia gas. We can balance this equation in a number of different quantities. Firstly, atoms. We can see that there are 2 atoms of nitrogen on the left-hand side and 2 atoms of nitrogen on the right-hand side, 6 atoms of hydrogen on each of the sides as well. Molecules, which gets a little bit tricky because there are 4 total gaseous molecules on the left-hand side and only 2 on the right-hand side. Moles, mass, and volume. So those are 5 different ways that we can look at balanced chemical equations. Just a bit of quick review here, as this will be very important. In 1 mole, there are 6.022 times 10 to the 23rd formula units, molecules, or atoms. This is, of course, Avogadro's number. And I included all 3 of those because it just depends on the type of particle that you're working with. Whichever of those is the representative particle, there are 6.022 times 10 to the 23rd representative particles in a mole. At standard temperature and pressure, 1 mole of gas takes up 22.4 liters of space. That's for any gas. No matter what type of gas it is, it will take up 22.4 liters. And then molar mass, we use grams for. So if we ever see grams, we know that we need to use molar mass in 1 mole. Okay, this is a chart from the book that I think is very interesting. It takes our balanced chemical equation for the production of ammonia and demonstrates it a number of different ways. Those are my dogs. I apologize. They're barking at someone at the door. So, if we look at the first row, we see 1 molecule of nitrogen gas, 3 molecules of hydrogen gas, and they react to form 2 molecules of ammonia. We can then count them as atoms or as molecules again, this time written in just English language as opposed to drawing diagrams. And it's the same ratio if we say 1 plus 3 yields 2 molecules of ammonia, or if 10 plus 30 yields 20. This is a situation that can kind of get tricky for some of the math folks, as we see that 1 plus 3 does not equal 4. It equals 2. Of course, the mass is the same, the number of atoms are the same because of the law of conservation of mass, but their arrangement has affected it in such a way that 1 plus 3, in this case, equals 2. You can look at Avogadro's number for molecules. We can talk about a balanced equation in terms of moles. You can see that the grams, when totaled up, are 34 on each side, as we would expect according to the law of conservation of mass. And then for gaseous liters, as one side of the equation, the reactants have 4 total moles of gas, and the product side has 2 total moles of gas, we would expect that as this reaction takes place, it will actually begin to take up less volume. If this goes to completion, we would start out with 4 moles of gas and end up with 2 moles of gas. And you can see on this bottom row that that would actually cause the volume to cut in half. So we can talk about a balanced chemical equation in a number of ways. Most commonly, we are going to talk about it in terms of moles. We can do equations to get, or conversions to get any of these values converted into moles. And then we can go from moles to some other piece of our balanced chemical equation, and then convert it to whatever other piece we need here. As always, check the comments for practice problems.